Hey guys, today we're going to be solving homogeneous second-order linear differential equations. The general format of a second-order linear differential equation is P of t times y double prime plus Q of t times y prime plus R of t times y equals G of t, in which P of t, Q of t, R of t, and G of t are all functions. Our equations today will be homogeneous, which means that G of t is equal to 0. Luckily, our coefficients are not those crazy functions that I just mentioned. Instead, they'll be simple constants a, b, and c. So in order to solve these problems, we need to make our differential equation have the form ar squared plus br plus c equals 0. This form is called the characteristic equation. A, b, and c are the same constants from our differential equation, and now we make y double prime become r squared, and y prime becomes r. Once you have this form, we solve for r just like a regular quadratic equation. Your value of r will affect your solution. Let's say the values of r you get are distinct, meaning they're both different. Then the general solution will be y equals c1 e raised to the r1t plus c2e raised to the r2t. If your r's are repeated, meaning they're both the same, so you get r equals, let's say 5 and r equals 5 again, then the general solution is y equals c1e raised to the r1t plus c2 times t e raised to the r1t. If the values of r are complex, meaning you had to use the quadratic formula, and you got r1 equals alpha plus beta times I, and r2 equals alpha minus beta times I, then your general solution is y equals e raised to the alpha t times the quantity c1 cosine of beta t plus c2 sine of beta t. The alphas and betas in our general solution are the same alphas and betas that we have in our values of r. Let's do a problem. Solve y double prime minus 3y prime plus 2y equals 0. The first step is to make the characteristic equation. Now we factor the characteristic equation. We get r1 equals 1 and r2 equals 2. So we have two distinct values, and this is the first case that was seen on our chart. All we have to do is substitute our values of r into that formula. So y equals c1 e raised to the 1t plus c2 e raised to the 2t. If we had initial conditions, then we would be able to find c1 and c2. This problem did not provide any, so we just leave the answer like this. Let's solve another problem. Solve y double prime of t minus 2y prime of t plus y of t equals 0. The first step is to make the characteristic equation r squared minus 2r plus 1 equals 0. We factor, and we get r minus 1 squared equals 0. Right away you can tell that you have repeated roots. r1 and r2 will be equal to 1. So let's look at our chart and see what our formula will be. We substitute our values of r into the formula, and as you can tell, the only difference we have in the formula compared to the one we used in the previous problem is that the second term is multiplied by t. So y equals c1 e raised to the t plus c2 e to the t times t.